Stay up late though it rains. It's good, but it is never the same. Never really the same.
So now we have uniqueness of solutions. Solutions. Okay? Also, this is also a theorem, by the way. Theorem. Okay? Alrighty, so for the uniqueness of solutions, there's a little bit, there are a few more requirements, or aka hypotheses, for this theorem, okay? So we have, I'll just divide it pretty simply into if and then. So the ifs are all hypotheses, okay? So for this one, we have if the equation that we're looking at is in normal form, okay? Is in normal form, alrighty, meaning like x prime is equal to f of t comma x. Okay, something like that. Alright, and then number 2, the second hypothesis, is that the right-hand side, so again, our function, f of t and x, the right-hand side is f of t x, and the derivative, partial f, partial x. It's important that we note that that's an x down here, not a t. So partial f, partial x, the right-hand side and this, so both of them have to be defined and continuous. And again, we'll say in a rectangle R, okay? In the rectangle, I'll just abbreviate, rectangle R. And again, rectangle meaning t stays in between certain values and x stays in between certain values. Okay, and then the third hypothesis is that the initial point, or the initial condition that we're given, okay, so the initial point, usually given as some like t naught, x naught, is in R. Okay, so it has to be inside for this theorem to even apply. Okay, so these are the 3 hypotheses for the uniqueness theorem. Okay, and then we have our then statements, which are conclusions, what the theorem actually guarantees us or tells us, okay? So we have 2 conclusions. The first one is pretty important. So number 1, there's one and only one solution to the IVP, to the initial value problem, okay? So this is the uniqueness part. That means that if we have these 3 things satisfied, if the hypotheses are satisfied for our uniqueness theorem, then the uniqueness theorem applies, and it guarantees, number 1, that there is one and only one solution to this initial value problem, okay? So there can't be like 2 solutions to this same initial value problem, okay? And then number 2, this one's a little bit less crucial, I would say. But anyways, this unique solution, exists until the solution curve, which is denoted as t going to some point on the tx plane, okay, until it leaves this rectangle. Leaves the rectangle, I'll just draw a rectangle here, rectangle R, okay? So like I said, number 2 is a little bit more trivial, but then number 1 is the main part of our, the main conclusion of our uniqueness theorem, okay? So I'll show you a geometric interpretation, like a graphical interpretation, okay? Because I always like to visualize things, so let's do one of those. So we have geometric interpretation. Interpretation is a long word. Okay, so geometric interpretation. So basically, let's say we have, I think an example would be good. So let's say we have some kind of function like this, or some kind of equation. There we go. So y prime is equal to, let's say, y minus 1, and then times cosine of yt. Okay? So here we have, this is our function of t and y, right? So this is in normal form, we're good. And then let's say we're given the initial condition y of 0 is equal to 2. Okay? So, let's see. What do we have going on here? So this is some ODE, right? That one there, and it's already in normal form, that's good. And we have that, well, our function, our f of t and y, seems to be continuous, right? It's not discontinuous anywhere, because cosine is a continuous function, as is this y minus 1. And also, if we take the partial of f with respect to the function, which is y, then we're going to get something like cosine of yt, and then plus y minus 1, and then times a negative t sine of yt, which again involves only cosines and sines, and none of these are discontinuous anywhere, so this is also continuous. So both of these, we can say f of t and y, and our partial of f with respect to y are continuous, okay? And are continuous everywhere, and it says like on which rectangle. This means everywhere, because it's not discontinuous anywhere, right? So it's continuous everywhere, and everywhere meaning like negative infinity up to infinity. This interval here, this rectangle, includes our initial condition, right? Or our initial value of 0, 2. This is like the point 0, 2. Our ty point includes the point 0, 2, so we're good. And the uniqueness theorem applies. So we can say uniqueness theorem applies, right? And what this means graphically, so let's say, okay, so we have this ODE here, right? And we don't have any solutions to it, but we can see from the problem, just looking by observation, we can say that y sub 1 of t is equal to 1, like a constant function. This constant function here satisfies our ODE, right? Just the ODE we're talking about, not the initial condition or anything. So here's our initial condition, here's the ODE. We're not trying to solve the particular solution or anything just yet. We're just saying, with reference to the ODE, what could solutions be? So one of the solutions, like I said, is y sub 1 of t is equal to 1. And the reason being is because the first derivative of 1 is 0, so that equals to 0, which is also equal to, when you plug in the 1 into the right side, 1 minus 1 times cosine of 1t. Yeah, it doesn't matter because this goes to 0. So that satisfies it, right? So here's one of the solutions, okay? And I'll show you where we're going to end up on the next slide. So we've determined that this is a solution to the following ODE when we have y minus 1 and then times cosine of yt. Okay, so this is a solution to this ODE. This is not a general solution, but a particular solution to that, but not to this initial value problem. So let's look at this graphically. So here's our ty plane, right? So this is 1, 2, 3, let's say 1, 2, 3. Okay, so this is 2, that's 2. Okay, so this thing here, this looks like just a horizontal line, right? So this is our y sub 1 of t, okay? And then, when we look at it, so remember we already said uniqueness theorem applies. Uniqueness theorem applies, okay? So then, if we look at our initial condition, this guy here, this is the point 0, 2. So 0, 2. So it's up here, right? This is our initial condition there. Alrighty? And then the uniqueness theorem basically just says that we cannot cross whatever solution this is up here, that this particular solution which satisfies the initial condition and the ODE, it cannot cross. Like, we can't have something like where it dips down and goes like that, because we would have this problem area, this intersection between our two solutions. But we cannot have that. We're not allowed to have that by the uniqueness theorem. Because it applies, it says that two solutions, so two distinct solutions may not cross at all, basically. Okay? So two distinct solutions, meaning they're not the same solution, they may not cross at all. Because if it does, so another part would be if two solutions, to an initial value problem, that is, to an IVP, do happen to cross or intersect by the uniqueness theorem, that means that they must what's called coincide. Okay, and coincide just means be one and the same, be one and the same solution. Okay, so what does that mean? That means, like, if we were to have let's say we were given this problem here. Okay, so this ODE, but instead of this initial value problem, let's say we were given y of 0 is equal to 1, let's say, okay? So if we had that, we would kind of just ignore this guy up there, okay? And now we have this solution, which is valid, right? That's still valid because we have the same ODE. And we have this initial condition sitting on the line. So because it crosses it at least one place, then our solution must be this y of t is equal to 1. It must be that same solution there. Okay?